least, Ryan Mann from University of Technology, all the way from University of Technology in Sydney. He's going to tell us about some interesting twist on a lot of the things we've been seeing this week with applications to transitions in quantum physics.
Thanks. So I'd like to start by thanking the organisers. It's been a great workshop and I've learned a lot this week. So everything I'm going to say is joint work with Michael Bremner, who's also at the University of Technology, Sydney. Okay, so just to motivate this talk. So the main problem in quantum computing, probably the most important problem, is are quantum computers more powerful than classical computers? And I'd like to know this to know if I'm wasting my time or not. So there's been like a lot of success in using methods from approximate counting, which underlies a lot of quantum physics, as I'll describe in a few slides' time. So there's been recent success in rigorously identifying complexity transitions in statistical physics models, which is the topic of most of this workshop. So for example, the independence polynomial in Jan and Lovász's talk, the matching polynomial in Leslie's talk, hypergraph colorings in Heng's talk, and the Ising model in Pishu and Huss's talk, and also I'll describe it in this talk as well. Is the font okay? Can like everyone read this? I think the colors.
Well, you color colorings.
Yeah. So okay. Anyway, so like the main question is, can we apply these techniques to quantum physics models, which typically are the same as the statistical physics models once you do some mapping, apart from they have complex values. So that's the main problem. So the recent techniques of Sasha and Patel and Huss have allowed us like an easy way to study these complex valued models. Okay. So what does a quantum computer do? So I'll describe this like more detailed in the next few slides, but just to give you an idea, we start with some easy to prepare state. So we're always going to consider the same state, and we'll just move all the complexity of preparing the state just into the quantum circuit. We can always do this. Then we apply some unitary, which is a sequence of... Okay, I think my thing's died. No, I'm just hovering. Sorry. Okay, so then we apply some sequence of quantum gates. So this is a quantum circuit diagram. So we're beginning with the all-zero quantum state. We'll then apply the sequence of H gates, which compose via the tensor product. And then we apply some collection of other gates. Just in this case, they're diagonal, but generally they don't have to be. And then we apply some other Hadamard gate. And this is doing the quantum computation. And then we're going to just measure and get the outcome. So we get some bit string as an outcome. And that occurs with the probability, which depends on this absolute value of this inner product squared, which I'll describe in the next slides. Okay, so what is a quantum state? So we're going to consider pure states in this. There's also mixed states, but that won't be relevant at all to this talk. So it's just a unit vector in a complex Hilbert space. And then it also has an adjoint, which we write using this notation. And this is just called a bra, and this general notation is called ket. So we're going to use these like throughout the talk. So just remember this is a vector and this is the joint. And then we can take an inner product between these. So the inner product just gives you the probability amplitude for observing some particular state, given like we started in some other state. And then the actual probability of observing this is just the absolute value squared. And then, okay, now how do we compose quantum states? So we've got two quantum states, then the total quantum state of those two systems is just the tensor product between the two. And then if we've got a state that has two subsystems and we can't separate it we can't compose it as a tensor product, then we say those quantum states are entangled. Okay, so here's an example of a quantum state. I guess you can try and write it as a tensor product between two states, but you shouldn't be able to. Okay, so we're going to consider like an easier representation called quantum bits. So we're just going to consider two-dimensional systems and build up from there. So these are fundamental object in quantum computing. So we write these zero states as just the 1, 0 vector, and this 1 is the 0, 1. And these we just call the computational basis states. And then we can just write any two-qubit system as like as a linear sum of these two things. And we have the property that like the absolute value of alpha squared plus the absolute value of beta squared just equals 1, because these correspond to probabilities. And more generally, we can write any quantum state in this system as a sum over bit strings, or the vector that corresponds to the bit string. So here we just ignore the tensor product notation, and it's just a tensor product of each one of these states individually, depending on the bit string. And then the probability of measuring a particular outcome x is just the absolute value of this alpha x squared. Okay, so how do quantum states evolve? So they evolve via some unity representation, which we call gates. So it acts on some, like, there's a gate in SU2 to the C, for just like some small constant C. It's generally like 1 or 2. And then a quantum circuit is just a sequence of these gates acting on n qubits. And we say that a set of gates is universal if it can generate a dense subset of SU2 to the C. So to C, you can just think of as 2 in this case. It won't make sense for 1. And then like an important theorem by Soloveic and Taev, which says that density implies efficiency. So if your gate set's universal and can densely cover SU2 to the C, then we can efficiently get like close to any point in SU2 to the C just with like a logarithmic number of gates. And it's sometimes useful to consider the Hamiltonian picture. So Hamiltonian is just a self-adjoint operator, and if we write e to the minus I ht, then we get a unitary matrix. So you can think of the quantum state evolving via time. So it starts in some particular state, we evolve through this Hamiltonian for a certain amount of time, and then we get a new state at that time. Okay, so now to relate this to...
Is this continuous or discrete time?
You could go continuous time, but if you're trying to build a quantum computer, you have to sort of plug in a real number. So it's sort of like arguments about whether things are discrete or continuous in like physics, for example. Okay, so the Hadamard test allows us to approximate these particular amplitudes. So it gives us some quantum algorithm where we have one particular bit, and the probability of measuring it up, for example, is given by this formula, and the probability of measuring it down is just gives the same thing with the minus sign. So the expectation value is just the real part of this amplitude. And then we can repeat this procedure a polynomial number of times, and then we can get an additive error approximation. With high probability, we can get additive error approximations to 1 over poly. And then we can apply a similar thing to the imaginary part. So the main thing is that just any, well, provided U is composed of like polynomial many gates, then we have some quantum algorithm which allows us to approximate any amplitude. Okay, so how hard is it to approximate a probability amplitude? So in the exact case, it's gap p hard. So this is, well, generally p to the gap p. And so this is just the closure of sharp p under subtraction. So any time I say gap p, you can just think of me saying sharp p hard. So it doesn't really matter. But the most important thing is it's outside the polynomial hierarchy for the arguments that I'll discuss later. So this diagram is generally representing like, well, complexity classes. The more things you're in is roughly how much easier the problem is to solve. So exactly computing these amplitudes is gap p hard, and up to relative error, it remains gap p hard. Up to additive error, it's BQP hard. So this is the quantum analog of the class BPP. So it's like a decision language. So essentially, approximating this amplitude solves all of the problems a quantum computer can solve. Well, all the decision problems a quantum computer can solve with bounded error. So it is, can we use the complexity of or this exact complexity to bound the complexity of a classical computer to simulate a quantum computer? So also, it's not worth noting we have factoring inside BQP. This is by Shor's algorithm, but not inside BPP. So this is like a big open question. Okay, so now to relate all of this to approximate counting. So an algorithm by Fenner and others says that for any problem in gap P, there's a polynomial quantum algorithm circuit such that this probability amplitude corresponds to the gap P problem under some normalization. So by the Hadamard test, that means we can efficiently approximate any problem in gap P, and also any problem in sharp P up to some additive error. But the problem is that this additive error is exponentially large. So it's not great, but we don't know of any classical algorithm for doing the same thing. So you could make some conjecture saying there's no classical algorithm for doing this. And this is exactly the same as saying there's a statement like BPP doesn't equal BQP. So what I think is weird, but I guess like some other people don't, is like that nature can solve really hard problems. So you can have like nature encode these probabilities of really hard problems, but you can't directly access the solution, or you can do a sample from it and try and get some estimate that way. Okay, so we could also consider the problem of trying to sample from some quantum computation. So we're going to do some quantum computation, and then we're going to look at the probability distribution at the end and try and sample from it classically. So this is a line of work by Aronson Arkhipov, and Bremner, Montanaro, and Shepard, and this is like a generalization of the argument. So the task is to approximately sample from some distribution for this but the quantum circuit has to be like a randomly chosen quantum circuit, but it's still producible in polynomial time. And you just want it to be approximately sample events close to some L1 norm. So if you conjecture that this probability is gaply hard to approximate up to a relative error on average, so it's saying that the worst case complexity equals the average case complexity. So if you assume this is true, then there's no efficient classical algorithm for sampling from these distributions unless the polynomial hierarchy collapses. So you have essentially got a separation between BPP and BQP, assuming the polynomial hierarchy doesn't collapse, and this conjecture is true.
So, I'm sorry, so U again is given by these quantum circuits, right?
Yeah. So there's like,
when you say hard, you mean hard in a classical sense, right?
yeah. Yeah, so up to a relative error. So how you randomly choose U depends on which scheme you're looking at. So for example, boson sampling is at random linear optical networks.
Are you going to give a hint as to what recent progress means?
So it's in the exact case. So I think Adam should be here somewhere. Adam Balland. So him and others at Berkeley have showed like in the exact case with continuous, so he needs some continuous argument that it's hard on average. I think that's right. Yeah, to exactly compute. So it's over like the similar sort of distribution, but in the exact case. Okay, so now I'm just going to divert back to the Ising model, which is what we've heard about, but I use like a slightly different notation, so I'm just going to go through this. So the Ising model is described by some weighted graph, and the vertices of the graph can be in two states, either like -1 or +1, or spin down or spin up. And the edges correspond to interactions between them. And vertex weights characterize external fields acting on each vertex, or each spin. And edge weights characterize the strengths between interactions between them. And then a configuration of the Ising model is just an assignment of each spin to one of two possible states. So that's what I before. So this is how we define it. It's in like a less combinatorial but more physics way. So the Ising model partition function is just like a weighted sum over all of these, of all configurations, and the weight is just given by sums of the edge terms and the vertex terms. And provided all of the edge terms are greater than 0, we say the model is ferromimetic. And if they're all less than 0, we say it's antiferromimetic. Okay. Now back to some quantum. So there's a quantum model called IQP circuits. So it stands for instantaneous quantum polynomial time, and I guess the instantaneous comes from these gates all being diagonal, which not exactly, but you could say that I can do these all at the same time. That's not like strictly true, but that's why they call it instantaneous. So we can define it by some Hamiltonian. We're going to define it by some Ising Hamiltonian over some graph. So you can probably guess where this is going to go. But the Hamiltonian considers like a sum over the edge terms given by some weight of x terms. So the x matrix is just given by this. So it's like a quantum version of the classical NOT gate. And then we have a sum over vertices of just like some single x gate. So vertices in this picture correspond to qubits. Vertex weights correspond to 1 qubit gates, and edge weights correspond to 2 qubit gates between them. So these can be thought of as entangling gates. So typically, if you write this in the circuit model, you get some circuits of the form. So you get some Hadamard gates. So this just takes the all 0 state and puts it into a uniform superposition of all possible bit strings. And then you apply some diagonal quantum gates, and then you apply these Hadamard gates again. Okay, so what's interesting about the IQP model? The probability amplitudes of this model are exactly equivalent to Ising model partition functions with imaginary weights. So now all of the arguments we had before about quantum circuits now apply to the Ising model with imaginary weights. And what's even more interesting is that these circuits are universal under post-selection. So post-selection just means that for some particular outcomes I can say, I definitely want a 0 here, and then I'm going to... So usually there'd be some probability of getting 0 on a particular qubit. Post-selection just saying, I'm definitely getting 0 on that qubit, and I'll ignore any other case. So meaning they're universal under post-selection would mean that approximating these amplitudes is as hard as approximating the amplitude of any universal quantum circuit.
Is that conditioning the distribution?
What do you mean by conditioning?
Can you get a
yeah,
probabilistic interpretation of post-selection?
So I guess you'd say with like some probability, depending on how likely the post-selection you want is, that you would implement the circuit you want. And otherwise, if it gives you, for example, if you measure 1 qubit and it gives you a 0, you could say, okay, that gave me the quantum circuit if I wanted. If I got a 1, I'd say that gave me some other quantum circuit. But the fact is that, like, since you're just considering the probability of something, you're just like forcing this 0 to exist anyway. So that still corresponds to an Ising model partition function. So you can take any quantum circuit amplitude and just write it as a partition function. And even if you've got some x gates here, you can just take the x gates inside, and that just corresponds to something like a pi/2 rotation on the field.
So which parameters in the Ising model do you make pure imaginary? The couplings or the magnetic fields?
Both. So they're purely imaginary in this case.
Yeah, and quantum computers can able to compute this, right? Or
You can't compute it. You can get an additive error approximation to this thing within 1 over poly, or if you get rid of the 2 to the n, it's 2 to the n over poly.
you can.
Yeah.
Okay.
I mean, it's not a great approximation, but it's everything a quantum computer can do in the decision language. Okay, so the question is, like, when can we approximate this like Ising model with complex values? So any time that we can approximate it, we have some good thing we can approximate the quantum amplitude. Okay, so now I'm just going to motivate the complex values. I probably don't need to cover this part, because but maybe I should start here. So the physical phase transitions are the real limit points of the complex zeros of the Ising model partition function. This is what Alan Sokal uses to justify studying complex models. Here's our justification. So probability amplitudes are proportional to partition functions with imaginary weights. So it implies that nature is described by these complex valued Ising models. And it means and it's also BQP hard to approximate up to additive error. So approximating these to an additive error, as I said, is just everything a quantum computer can do essentially, except for the sampling thing. Okay, so now we're going to see what happens when we apply the sampling argument to IQP circuits. So you're going to approximately sample from some random IQP circuit, and this is on the complete graph or a sparse graph where each edge is chosen with some probability log the number of vertices or number of qubits over the number of vertices or qubits. And then the weights are chosen from some discrete set, I to the pi over 8, and then from 0 to 7. And the conjecture is that if Z, the Ising model partition function with these weights, is gaply hard to approximate up to a relative error on a constant fraction of instances, then there's no classical algorithm for sampling from it unless the partner hierarchy collapses. So understanding the complexity of random complex Ising models is important for separating quantum and classical computation. This is up to relative error. Okay, so how hard is it to approximate the partition function? So Alistair and Sinclair, firstly, in '93, gave an F-pras for the Ising model partition function along the ferromagnetic axis. And that's for any field. This picture is going to completely ignore fields, as I thought it was like quite complicated already. And it's going to ignore quite a lot of results because there's so many, I can't cover them all. So this diagram is just going to describe the complexity in terms of the interaction strengths, or the maximum of these.
So just to go, in your model, there are vertex-dependent fields, right?
Yeah.
So they can be very different on different vertices.
Yeah, so these are like randomly chosen from discrete set. You can make the argument work for several other random choices. They just chose one that like was quite natural. Okay, so then so Alistair, Piyush, and Thurley gave an FP-TAS somewhere along the antiferromagnetic line up to the point where you get decay of correlations to some boundary degree graphs, and you get up to the uniqueness of the Gibbs measure. And then Jing-Shen, Alistair, and Piyush gave an FP-TAS for some zero-free region surrounding this, so they could apply the Barbanach argument and get an FP-TAS up to here. So it shows that this also corresponds to the region where the zeros become dense. And then Sasha and Soberon gave an I guess this is the correct notation, a quasi-polynomial-time approximation scheme.
We didn't call it that way. Well, okay.
What did you call it?
We didn't call it at all.
Okay. Well, I mean, it's for the graph homomorphism partition function, but you can do like some reduction to this without fields. So this corresponds to the zero-free region around here. Also note, this corresponds to the quantum line. So along here is everything we care about in the quantum case. Patel and Goose extended this to a FP-TAS. And then in this talk, we're going to extend it to an FP-TAS, and then we're going to include some field. So it's a small field, but it's at least one step towards that. You can see. Okay, and then you just see it. You can read my text, right? Read the writing right.
Oh, there we can.
Okay, yeah. Yeah, I can't read it myself, so it's quite bad. Okay, so Sly and Son, and then independently Galnis, Stavankovic, and Vigoda gave hardness proof along just outside of this interferonic regime. So this gives like an exact transition point, at which things go from easy to hard. And then in this talk, we're going to do the same thing for the imaginary axis, although we're not actually tight, but we're like within some constant of being tight.
And so this is for zero field to hardness also.
I stated for zero field, but I think it should hold for field as well. I think the constants will just change somehow. Okay, so let's just state the results. So our main thing is we get a deterministic polynomial-time algorithm for approximating the complex valued Ising model on graphs of maximum degree delta. When these interaction fields between the field and the vertex things are basically bounded close to zero, and that's bounded by this constant, which comes from Barbanok's monograph. So you can get some values here, but the main important thing is this goes as like roughly 1 over the maximum degree of the graph. And then we're going to convert this to quantum to say what this is in the quantum case. And it says we get an efficient classical algorithm of probability amplitudes of so the IQP form for graphs of maximum degree delta when the interactions are bounded by 2 arcsine for this thing, which also goes as like 1 over the maximum degree. So to convert this to the physicists, on a hexagonal lattice we can simulate pi over 23 rotations. So you can think of these fields as just rotations in the quantum circuit, or rotations in SU2 and SU4. And on the square lattice we can simulate up to pi over 29 rotations. In general, like 1 over delta rotations. And then this algorithm is also almost optimal, because we get hardness results if we allow rotations up to some constant which also goes as 1 over the maximum degree. And at this point, it's gap p hard up to approximate these amplitudes up to relative error, and BQP hard to approximate them up to some additive error.
So are these numbers for special lattices of any importance? Like, would you be interested to like get, I don't know, pi over 15, say, or something like that?
For like these lattices we are, so this is like, this result was just for any, I guess, degree 3 graph. This is any degree 4 graph. We're just playing them, but yeah.
Would it be of any interest to tighten it for special lattices?
Yeah.
It would.
Yeah. So I think there's several papers that sort of do this, but it's hard to like.
Because I think you can.
Yeah. Yeah, especially for like the square lattice and hexagonal, that shouldn't be like the worst case of like degree 4 graphs.
Right. So square lattice, I think, behaves like a graph of degree 3, basically.
Okay. Yeah, I could see that. Okay. Okay, so roughly how does our proof work? I'm not going to go into this too much detail, as you've probably had enough of this already. But the idea is we reduce it to a pinned graph homomorphism partition function. So the partition function, or the graph homomorphism partition function is defined similar to an Ising model, except when we're going to say that sometimes we're going to not sum over all configurations, and we're going to allow some configurations to be fixed. And this is going to allow us to implement some external field by just adding an edge to every vertex and then fixing the other spin. So Sasha and Soberon gave a quasi-polynomial time for approximating the graph homomorphism function when these matrix entries are also bounded by 1 over the maximum degree using Barbanok interpolation or Barbanok's philosophy. And then Patel and Hoos gave an improvement to polynomial time, and the idea is they're expressing the coefficients as connected induced subgraph counts. Okay, so just to sketch the proof quickly, we apply a slight extension of the Patel and Hoos approach to pinned graphs. So we just, well, the proof basically follows directly. We just have to say that we can now allow us to pin vertices to particular spins. And then I went about proving like a zero-free region for the pin case, but in Sasha's monograph, actually the proof is by induction on like pin vertices, so I didn't have to do any work, which is great. So this result just gives us a polynomial-time approximation scheme for the Ising model when these weights, and we just get some extra +1 in the maximum degree here from adding all of the vertices, adding all the edges to every vertex to give the field. Okay, and now to sketch our hardness proof. So the problem is that this only works for multi-graphs, but I think we should be able to extend it to number graphs. Okay, so the first statement is that it's gap p hard or BQP hard on graphs of maximum degree 3 with imaginary weights bounded by pi/2. So this sort of simulates all the rotations you could do on a quantum computer. Okay, now we're going to consider the worst case graph, and then we're going to consider, so this is going to be my worst case graph, or some graph that could be the one you want to simulate. We're going to consider the k thickening of this. So the maximum degree of this k thickened graph just becomes whatever it was before. So for example, 3 is the hard case, and then times k. And now if we allow rotations up to pi/2k on this graph, these all add together, so we get the exact same pi/2 thing we want on here. And then we rewrite this in terms of k, and then we get 3 pi/2 delta. So you also get this 1/delta scaling. So this implies the gap p hardness of for relative error and BQP hardness to additive error of approximating the Ising model partition function when our weights, well, they have to be imaginary, are bounded by 3 pi/2 delta. Okay, so what do these results imply? So we get some quantum complexity transition, roughly at 1 over the maximum degree, where additive error approximations transition from P to BQP hard, and relative error approximations transition from P to gap P hard. So you can interpret this in a physics model as you could say it's a classical FP task for some short time-evolved Hamiltonians. So if we can imagine T corresponding to the weights of each of these vertices, at T equals 0, they don't do anything, and then as you increase T, we can approximate the Hamiltonian, and then you get to some point where you just can't. It also corresponds to quantum circuits with band interference, because we know this amplitude can never be 0, because that corresponds to a 0 of the Ising model partition function. So it's saying what classes of quantum circuits can we construct such that the interference can never completely cancel, or go beyond cancelling, as in go negative, for example. And also quantum circuits with limited teleportation. So to give you an idea of teleportation, you can imagine having 2 qubits, entangling them together, and then measuring 1 qubit, and then look at the effect of that on the other qubit. You can use this to teleport gates and things. So we know we have limited teleportation because an X gate just gives you a direct 0. So if we could construct our circuit to teleport things through and through, just to construct one X gate, then we'd know we could get to a 0. So we know that can't happen. And this also gives a formal relationship between the geometry of zeros and the complexity of quantum computing. Okay, so can we apply this to other probabilities? Because it seems like if your system is such that we can compute one amplitude, then we should be able to compute the other ones. So this isn't obvious, and we haven't managed to solve this yet because we require X gates, which correspond to like pi/2 rotations, so we can't do those anyway. And we know that just having an X gate on just a 1 qubit thing just gives us a 0. And this means the Ising model partition function is 0. But maybe we could use decay of correlations to get around with this and maybe have some argument which works regardless of what the field is. So I guess you could just say, like, even if we just had like a completely separable system of several qubits and apply X gates on them, there's no correlations, but somehow this algorithm won't work. Okay, so the open problems in this. So we'd like to identify an exact quantum complexity transition point. So we know in the real case, for like the Ising model, we know an exact transition point, and we'd like to be able to do the same along the imaginary axis. We'd also like to experimentally or like physically probe the transition point, as we expect at some point there's got to be some physical properties of this system that means that it's easy to simulate to go to hard. So maybe the entanglement dynamics go from short range to long range, or there's some interesting physics there. And then also we'd like to extend these arguments to other probabilities or sampling problems, maybe using like things like decay of correlations methods. And then we'd also like to apply these techniques to many body physics, so in the case where the Hamiltonian doesn't commute. We haven't had much success doing this though. And also, I like to understand the relationship to other methods. So Monte Carlo, decay correlations, and then other methods from quantum, which we can now compare to. So the tensor network methods and stabilizer rank method. I'll just describe what these are in a second. But the main thing is, like, the people I spoke to who work on these say that they can't simulate the system using like their techniques. So a stabilizer rank, in like a combinatorial thing, you have, see, the theorem of Jaeger, Verding, and Welsh says that the top polynomial is hard apart from like 8 special points. And they correspond to, like, some of them correspond to, like, on the Ising model partition function. And then we're going to say what quantum circuits give you those. So it gives you a discrete subset of SU, I guess like 2 to the n, called the Clifford group. We can efficiently compute any of these probabilities. So the stabilizer rank says we can take like any, like, say, non-stabilizer circuit or something that's not easy to compute, and we can write it as a sum. And generally this inherits exponential complexity as you're decomposing every gate like twice. But in certain circumstances you can say, okay, I can like do this and I have to do it a logarithmic number of times. Okay, so in the workshop program, it mentions connections to the Lovász local lemma. So I'm going to have a go at that. So maybe I'll just like skip this part. So the Lovász local lemma says that we have some sequence of events, and with each probability occurring less than p, and each event depends on at most delta other events. So provided p is bounded by this thing which goes like roughly 1 over delta, then the probability of none of the events occurring is greater than 0. So this is useful in existence proofs if we've got some collection of random graphs, for example, and we know that the probability of something occurring is non-zero, then we know there's a graph with that property. Okay, so can we take this into a quantum Lovász local lemma? So there's already a quantum Lovász local lemma, but it's a completely different flavor. So in our scheme, we're going to say an event is just measuring the outcome 1 on qubit k. Then the dependence is just the maximum degree of the graph. And then provided we have these things on the weights, so you can imagine doing the vertex weights first, and that gives you the probability before you do your quantum circuit of each thing. Then the probability of getting the all 0 state is greater than 0, or you could say the probability of no events occurring is greater than 0. So it gives you a problem of like when can you decide if interference cancels out, like an event. So this is NP hard in general. I think maybe sharp P hard. Okay, so maybe we can try and find an application of this. So this is like quite far off, but maybe what's existence in quantum physics mean? So for example, maybe in quantum field theory, you can map the probability of getting some particular particle to a transition probability in the quantum computational model. And then provided it satisfies these certain things, then we know there's like a non-zero probability of detecting a certain particle. So maybe there could be some experiment where you want to say, can I get this particle out of the experiment? And that happens with like some like 1 over 1,000 probability or something. You'd never see it. But provided that your experiment satisfies this, then you could say, okay, there's like a non-zero probability of seeing this particle. Okay, so I think I'll end there.
Any questions?
So do you think quantum computers are real?
I guess what do you mean by real?
Yeah, so for example that Shor's algorithm will be implemented to factor numbers with several hundred digits.
Well, I'm just going to guess. So I don't think anyone knows the answer, but I'd say yes. Okay. I'm like quite optimistic because I think there's like several things in physics where someone will describe some principle that you go, okay, that works, but like you'd never be able to build it, and then they end up doing it. Like, I think it's really hard to predict how technology advances.
So how would you respond to that argument that you need such a precision of quantum circuits that physics laws basically don't hold to that precision?
Well, I mean, you can build small scale ones, and I guess the problem is like an engineering challenge. And like I guess like 200 years ago, if I said like I could build like this laptop, then like I think people wouldn't believe me then. So, well, I don't know the answer, but I think it could go either way.
Well, they would accuse you of witchcraft, that's more likely. But
Yeah.
There's a New York Times there's New York Times article in the 1920s or something where somebody was proposing rocket propulsion, and there was an editorial or something which said like Professor so and so seems to be unaware of the knowledge that is ladled out daily in high schools. And 40 years later, they published an erratum saying that the Times regrets the answer.
Any more comments?
So the transcription that you described, so the imaginary thing is only for IQP, but if you allow everything, then you get all of BQP.
No, so it's just for IQP, but since you're only approximating amplitude, it's for all of BQP.
So if you allow...
So if you imagine other complex, then you can map some quantum circuit, but I'm not sure it will be universal.
Okay.
So you can take any model from like the Ferner theorem. So you could do an antiferrometric Ising model, and then you know the exact transition point. But the problem is when you do this, as your quantum circuit's got some weird structure to it to implement this like antiferrometric thing that you want. So you could say, okay, I know the complexity transition of this quantum circuit, but it's like very unnatural.
Great. Well, that wraps up the workshop. So I want to thank Ryan again, and also everybody for contributing to it. It's been a nice week.